Yeah, so this is the last recorded lecture for, well, at least my part of game theory and optimization, so the game theory part. And what I'm going to do in this recording is talk a bit about you could say, a next refinement, or at least the next equilibrium notion, which is called exposed equilibrium. And you could think of this as an intermediate one between Bayesian-Nash equilibrium and dominant strategy equilibrium. So dominant strategy equilibrium is an exposed equilibrium, and an exposed equilibrium is a Bayesian-Nash equilibrium, but it has its own definition. So it's good, I think, to have seen that, because it's actually used quite a lot. And we're going to look at that in the context of a model that we have seen before, which is the sales of one single indivisible item. And well, the setting is as before. So we have n agents and one indivisible item for sale. And agents have valuations, but the type of auction, we already looked at the first price yield bid auction in that context, but there's another auction format which is called the victory auction. And that is the one we're going to discuss next. It's also known as second price yield bid auction. And what it is it's in essence, literally the Vickrey-Clark growth mechanism, but then applied to the sales of one particular item. So what does that do? We have this single item. So we have the bidders, and each bidder has a value for the item. So for ownership of the item, as before. So in general, the VCG is a very complicated thing, of course, but here, because there's only one item for sale and it's indivisible, there are only n possible allocations. Maybe you can give it to bidder 1, or to bidder 2, or to bidder 3, etc. And the valuations are such that if somebody else owns it, that is value 0 for you. And if you own it, then you have this valuation VI. So that is the setting. And that means that, well, that bids in this auction reduced to simply bidding a number between 0 and 1. And so that means that valuation functions, or reported valuation functions, are very simple objects. In this case, are simply one specific real number. And yeah, so again, we assign the item to the bidder with the highest bid, which are made simultaneously. So you assign to the bidder with the highest bid. If there are more of them, yeah, you just select one of them and assign it to that person. And the payments are, well, so if you don't get anything, you don't pay anything. But if you are assigned the item, then you pay the second highest bid. The maximum overall BJs of J other than I. Maybe this requires a bit of explanation. So, for example, let's say the valuations are, well, maybe I can explain it in terms of bids. Let's say there are 5 bidders and these are their bids. Then what does VCG do? Well, it assigns to, so it chooses the allocation that maximizes total reported utility. So if you assign it to 1, for example, then what is the total reported utility? Well, it's 10 for a bidder 1, plus, yeah, then 4 zeros, right? Because the other ones get nothing. And well, implicit in the assumption that you only report a value for ownership of the item implicitly means that if anything else happens, then that is value 0 for you. So this would be 10. And of course, if you give it to 2, then that would result in something like this, of course. So that's 7, etc. So it's easy to see, of course, that you should assign to bidder 1. That's clear. But now the payment. So what is the payment? The payment is your externality, right? And so what would that be? Well, if you would restrict the allocation process to just these 4 people, what would happen then? Then the total utility would be maximized by assigning it to bidder 2 in this case, right? Because that will give you a value of 7 plus 0 plus 0 plus 0, which is 7. And assigning it to 3, for example, would give you 0 plus 4 plus 0 plus 0, which is 4, right? So in that case, if one would not be present, then total utility would, at least reported utility, would be 7. And so what do you subtract? You subtract the current total utility of these 4 remaining people, and that is in fact 0, because currently they don't get anything. Only bidder 1 gets the item, and the reported value of the other ones is 0. So what is your payment? 7 minus 0, which is 7. And yeah, that is of course identical to simply the second bit. So that is where this formula comes from. It's the externality in terms of VCG, right? But in this specific simple economic environment, that is in fact the same as simply paying the second highest bid. That's where this formula comes from. Okay, so this is the auction format. And yeah, so we have the theorem from VCG, which says that reporting the truth is a dominant strategy in this setting. And of course, if everybody does that, then that is an equilibrium in the sense that you cannot do better. So given that the other ones report the truth, it is a best response for you to tell the truth as well, because telling the truth is always a best response, no matter what. So, okay. Having said that, so this particular auction format allows for many, many other types of equilibria. We're not going to look at all of them, but we're going to look at one of them. And it's not an equilibrium in dominant strategies, because you can prove, and that is actually the Green-Lafont paper, that if you want to have dominant strategy equilibrium, then indeed truth telling is in some sense the only option. But there are many, many what are called exposed equilibria. And that is what we're going to look at. So what's an exposed equilibrium? An exposed equilibrium is a strategy profile in with the property that if you take any realization, so you just take realized evaluations, evaluation functions, and if you take such a realization, then you can compute the bits, right? So if beta 1 has a valuation function of v1, then you can use the strategy that he is using to then compute his reported evaluation function. And you can also do that for all the other agents. And of this, you can actually compute whether or not it is a Nash equilibrium, because now the valuations are known. So you can compute utilities, and so you can check whether your bid maximizes your expected payoff or not. So that, and if that is the case for each of the agents, then we have an exposed equilibrium. Yeah, so of course it's clear that if you have a dominant strategy equilibrium, that is indeed an exposed equilibrium. So dominant strategy equilibrium is indeed an exposed equilibrium, because in a dominant strategy you play best response against anything. So in particular against what other people are bidding in the equilibrium. And it's also true that an exposed equilibrium is a Bayesian Nash equilibrium. Why is that? Well, so you can also think of exposed equilibrium as what is called a no regret equilibrium, meaning that you have to think of your strategy in advance. So you know, ex ante, so to speak. So before you even know your own valuation, you decide what to do, but in the sense that you say, if this is my valuation, then I would bid such and such. But what does and you do that before you know anything about valuations. But what is the exposed equilibrium? It says that, well, if you make your bid, and then after the fact, you observe the realizations and you see what happened in the auction, given the bids that you made, would you then have regrets? So would you change your bid after the fact? And if that is not the case, then we have an exposed equilibrium. So that really means that you bid currently without knowing the valuations of the other ones, but then after everything made a bid, you observe, you get to see what the valuations were and what the bids were. And then if you then would not have an inclination to change your bid, then you have an exposed equilibrium. So that means that in all eventualities, of course, you bid a best response. And that means then also on average, so if you average over, you know your own valuation, but you average out over the other ones, that should also be then a best response on average, because you bid best response in every eventuality. Okay. So that is in short the connection between the other equilibrium notions, but what we're going to do for the rest of this talk is to simply look at one. And the one that we're going to look at is called wolf and sheep. So that means that one of the bidders is wolf and all the other ones are sheep. So let's say bidder 1 is the wolf, and what does he do? Well, he has a bid strategy that is very aggressive, namely he always bids 1. So his valuation is 1, he bids 1, but also if his valuation is a half, he bids 1. If it's 3/4, he bids 1, and even if his valuation is 0, he bids 1. You could actually draw that. So if here you plot valuations and here you plot bids, then truth telling of course would look like this. But this strategy is simply the constant strategy that has bid 1 regardless of the valuation. So that's how you have to think of that. It's a constant bit function. And all the other ones are sheep, so they bid 0, regardless of their valuation. And what we're going to argue is that the combination of these bid functions, so the constant bid function 1 for the wolf and the constant bid functions 0 for all the other ones, constitutes an exposed equilibrium. Why is that? Well, so take any realization of valuations, then the resulting bid profile is actually this one over here. Is it 1 and then a lot of zeros? For the obvious reason that S1 V1 is always 1, regardless of V1, and that SI VI is always 0, regardless of VI, if I is not 1. So you get this. So how do you check that this is a Nash equilibrium? Well, you're going to look at one of the players. Let's say we start with the wolf, and the wolf is facing a bid profile of lots of zeros. So you can compute his utility if he wins. We've got his valuation, V1. And what's his utility if he wins? Well, his valuation, his true valuation, minus the bid. So minus the payment. So the payment was, if you recall, the maximum over all BJs, where J is not 1. In this case, that is a maximum over lots of zeros. So the payment is 0. He gets the item for free. And if he makes a bid that loses, then his utility is, of course, 0. He doesn't get the item, but you also do not pay. And yeah, so V1 is, of course, largely equal to 0. So making sure that you win is one of your best responses. How do you win? Well, for example, by bidding 1. So any bid larger than 0 is a winning bid. Among those, 1. So you get many best responses, but 1 is one of them. So that's what it says here. In particular, bidding 1 is the best response. Now for the sheep, that is a similar line of reasoning. But now the bid profile is 1 and 0, 0, 0, 0, 0. All the sheep have 0 bid, but the wolf is now also one of your opponents and he bids 1. So if you win, then what is your valuation, or your utility, sorry, what's your valuation subtracted? Well, your payment is now the maximum over the BJ's, where J is other than I, but that is now the maximum over the entries in this vector here, which is 1. So you pay 1. And if you lose, then of course your valuation is 0. And this here is at most 0 because Pj is between 0 and 1. So you see that losing is indeed one of your, losing is one of your best responses. And the way to guarantee that is, for example, by bidding 0. Anything smaller than 1 will do. But one of the options is then to bid 0. And that is explained here. Maybe shortly efficiency. This equilibrium is not efficient. For example, if V1 is, so there's a realization, for example, where V1 is a quarter and V2 is half, and all the other ones are, let's say 0, whatever. Then in the Wolf and cheap equilibrium, of course, 1 wins, so 1 is the winner. But as you can see, V1 is not the highest valuation. So there are cases in which the allocation is not efficient. And that means that if there is a realization for which the allocation is not efficient, that means that in total, the allocation is not efficient. That's how we say that. So the equilibrium being efficient means that it's efficient in any realization. Okay. I think that was it for the slide. So that also means that this is it for this part of the course. So I wish you all a very good time with the OR part, and yeah, we'll maybe see each other in somewhere in one of the other courses, and at least probably before the exam and with the presentations. So see you then.